Hello everyone, we're going to talk about section 5.2, which is going to be about compound interest. So in our last section we talked about simple interests and we also went over the basics of financial math. So now we're going to go over compound interest, which is going to be a little bit more challenging versus simple interest. So we see with annual compound interest, you can earn interest on both your original investment and on your previously earned interest. And with simple interest, you're only earning interest on your original investment. And so we can see an example here with our simple interest. So if we're earning 5% interest and we originally invested $1,000, then we're going to get an additional $50 we see every year. But with compound interest, when we have 5% interest, we calculate for that first year, which is also known as simple interest since we're thinking about a year or less. So we calculate the first year and that's going to give us $1,050. Then we're going to calculate 5% interest on the $1,050. So you're taking whatever end value you had from the last period, and then you're calculating your interest on that value. So instead of our simple interest, which was just calculating the same value again and again and again, just adding them up, now we're taking into consideration the value that we had at the end of the last period. So this chart shows us just how our investment grows with compound interest versus simple interest. So obviously we see here that with compound interest, we're going to be earning more than we do with simple interest by the end there. And that is because you're taking whatever percentage you had now on the value that you have with interest. So obviously that value is going to be greater than your original investment. So you'll be making more money with compound interest. So we have if P dollars are invested at an interest rate I per period, and the compound amount or the future value A after n compounding periods is A is equal to P times 1 plus I to the n power. So when we talk about n compounding periods, the periods that we talk about with our simple interest was usually, a year, a few months, something along those lines. With compounding periods, we can do anything from a year to monthly, semi-annually, quarterly, or even daily. So it's important to know how often you're compounding within your year-long period. Also, we have our interest rate I. P dollars is considered our principal or maybe the present value, and then we have A, which is going to be our future value. So this is the equation that we're going to use to compute our compound interest. We also use n as compounding periods, but if we set n equal to t, and if t is the number of years in this case, then we get that our compound interest is just A is equal to P times 1 plus R or I. In our case, I just rewrote it as R since that's what we know from our simple interest, to the t power. But our simple interest would just be A is equal to P times 1 plus R times t. So we see if we kind of just make our i's r's, which is essentially the same thing, it's still just our interest rate. And then if we set n equal to t, we see that these equations are fairly similar to each other. All right, so let's do our first example. And this is going to be checkpoint 2 in your book. So we're going to suppose $17,000 is deposited at a 4% compounded annually for 11 years. So we want to find the compound interest. First, let's just declare what each of our variables are. So if we want to find P, or our principal, that's going to be 17,000. Then we want our investment rate, I, which is 4%. So we write that as 0.04 since we want it in decimal form. And then we're compounding annually for 11 years. So our value of n is going to be 11. All right, so we found P, I, and N, which are all the things that we need to find for our compound interest according to this equation here. So let's just rewrite our equation so we don't forget. We have A is equal to P times 1 plus I to the n power. So now let's plug all our values in. We get that A is equal to 17,000, 1 plus 0.04 to the 11th power. Now we can simplify it as much as possible, so let's add what's inside our parentheses. So we can get A is equal to 17,000 times 1.04 to the 11th power. And if you'd like to calculate this on your own, you can pause the video. But you should have gotten $26,078. And that'd be your compound interest after 11 years. So now we want to find the amount of interest earned. So to find the amount of interest earned, all we need to do is subtract our initial investment from our compound amount. And our compound amount is going to be that value that we just solved for, that 26,000. So we'll write that $26,078. So that's our compound amount. So that's all we need to do. So we can just say $26,078 minus 17,000. And what we get is $9,078. So the amount of interest that we earned was $9,078. All right, on to example 2. This is going to be number 19 in your book. So we want to find the interest rate with annual compounding that makes the statement true. We have $3,000 and it's going to grow to $3,606 in 5 years. So we want to use the same compound interest formula as we had before. It's just that now we don't know what our value of I is. So we're solving for our value of I instead of our value for A, since we know what A is. So let's write out all of our variables so we know that P is going to be 3,000. A will be $3,606. We're doing annual compounding for 5 years, so N is just equal to 5. And we're solving for I, and then we want to remember that our equation is A is equal to P times 1 plus I to the N power. All right, so let's plug all these values in and let's solve for I. So we get $3,606 is equal to 3,000 times 1 plus I to the 5th power. Now we're solving for I, so we want to simplify this as much as possible. So we're going to divide by 3,000. And in this case, we are going to get 1.202 is equal to 1 plus I to the 5th power. And we want to get rid of that 5th power, and we know how to get rid of it. We'll just raise each side to the power of 1/5. So then these values will cancel. I'm going to pull this up here. So now we have 1.202 to the 1/5 power is equal to 1 plus I. So now we've simplified down, so we don't have anything really manipulating I anymore. We'll just need to subtract that 1, but we really want to find what 1.202 to the 1/5 power is. So if we end up calculating that, we end up getting that that would be 1.0375. And that is going to be equal to 1 plus I. So we want to simplify I, so we're just going to subtract 1 from both sides. And we get I is going to be equal to 0.0375. Or since we can rewrite this as our actual rate, we know this is equal to 3.75%. All right, so we know that to make this statement true, our interest rate would have to be 3.75% in order for $3,000 to grow to $3,606 in 5 years. All right, So like I said before, interest can be compounded more than 1 year. It doesn't necessarily have to be every year. So we can have some common compoundings would be semi-annually or 2 periods a year, so twice a year. Quarterly, which will be 4 periods a year, 4 times a year. Monthly, so we'll have 12 periods a year, so it'll be every month, so 12 times a year. And then we have daily, which is obviously 365 days a year. Now, when we have annual interest compounded in m times per year, so any amount of times per year, the interest rate per period is understood to be I divided by m. So your new I value is going to be I divided by m. So if you're given 0, or if you're given 4%, which is 0.04, and you're compounding maybe twice a year, then your interest rate will be 0.04 divided by 2. So that's what kind of our m times a year plays here. So here's another example. If your investment rate is 3.5% compounded monthly, then your new interest rate is going to be 0.035 divided by 12. So your new interest rate will be whatever initial interest rate you had divided by however many times that you are compounding that year. So you're always going to do that now whenever you see that we're compounding multiple times a year. All right, so let's put it into practice. We have with principal equal to $20,000 and an interest rate of 1.6%, we want to find the value of investment for 1 year and interest compounded according to given periods. So we're doing it for 1 year, but now we're checking with annually, semi-annually, quarterly, monthly, and daily. So once we do this, we know that for annually, our p-value is 20,000. Our interest rate, which is 1.6, is going to be 0.016. In this case, since it's annually, this means 1. So this is technically 0.016 divided by 1. So we would just write 0.016. And we know that n is equal to 1 since it's annually. We're just doing this for 1 year. So now we can compute our future values. So we get that a is equal to p times 1 plus I to the n power. And with our variables, we get a is equal to 20,000 times 1 plus 0.016 to the first power. Then, if we compute this, we just get that this is 20,000 times 1.016, since 1 plus 0.016 is going to be 1.016 to the first power, so that's just the same value. And when we multiply these together, we're going to get $20,320. All right, so that's what we get if we did this annually. Now let's do semi-annually. So we have the same p-value, still going to be 20,000. Now since we're doing this semi-annually, this means 2 times a year. So that means that m is going to be equal to 2. So our I value is going to be 0.016 divided by 2. And then our n value is also going to be equal to 2. All right, so we know our equation already, so let's just jump right into it. We have a is equal to 20,000 times 1 plus, and now we're going to have 0.016 divided by 2 to the second power. All right, so now since we have this value, I highly encourage you to go ahead and calculate this value on your own. And if you had, you should have been able to get $20,321.28. All right, so we see that now when we're compounding semi-annually, Still pretty close to our annual compounding, but we do make a little bit more. So now let's try it with quarterly. So same thing as before, we have P is still going to be 20,000. Now our I value, since quarterly means 4 times a year, we're going to have our interest rate divided by our numbers, or our number of periods per year, which in this case will be 4. And then our N is the number of periods per year, so that's also going to be 4. And once again, we still know our equation, so let's plug everything in. We get A is equal to 20,000 times 1 plus 0.016 divided by 4 to the 4th power. All right. So once again, I invite you to calculate this value on your own. And if you had, you should end up getting $20,321.93. So this is really similar to our semi-annually value, which is also still similar to our annual value, but we do see that it's increasing the more times that we compound per year. Now let's try out monthly. So same p-value here, still 20,000. Our interest rate is 0.016 divided by, monthly is 12 times a year, so divided by 12. And our N is going to be equal to 12 as well. And let's scoot this over just a little bit. There. All right, so we can plug this into our formula. So we get A is equal to 20,000 times 1 plus 0.016 divided by 12 to the 12th power. So I invite you to calculate this on your own. And if you do, you should end up getting $20,322.36. So we see this is still larger. Every time we compound more often per year, we end up with a larger value, but not much larger than just our annual value. So we see if we do compounding monthly, we're going to end up with just an additional $2.36 as opposed to annually. And let's do our last one. Let's try out daily. So we know our p-value is still 20,000. I is going to be 0.016 divided by 365, since there's normally 365 days a year, unless it really specifies that there's been a leap year, you're always going to go with 365 days a year. Then our N value is going to be 365. All right, so let's plug everything into our equation here. We get A is equal to 20,000 times 1 plus 0.016 divided by 365. My little stand here just fell. All right, I think that's good now. Okay, it's locked in. Hopefully that doesn't happen again. All right, so we had 0.016 divided by 365 to the power of 365. All right, so I invite you to calculate this on your own as always. And if you do, you should end up getting $20,322.57. All right, so if we compound daily as opposed to annually for just 1 year, we see that our end result, if we compound daily, will get us an additional $2.57 by the end of our time. So we see that compounding more often in a certain period will give us more money in the end. Maybe not that much more, but still more. All right. So we have the idea of compounding more and more frequently leads to a method of computing interest called continuous compounding. So since people have seen now that compounding more times a year will get you more money, they decided to make up this new theory called continuous compounding. And so we want to find, not found, compound amount for $7,500 invested at an annual rate of 2.07%, compounded continuously for 3 years. So if we're going to compound continuously, we're going to use our equation of A is going to be equal to P E R T. So if we use this equation, and we have that P is equal to $7,500. Our rate is 2.07%. So our rate is going to be 0.0207%, or just in decimal. And we want to do this for 3 years. So our time in years will be 3 years, or just 3 in this case. All right, and this is our equation for continuous compounding here. So now, since we have all of our different variables, all we need to do is plug in all of our variables for A. So we get that A is equal to $7,500 times E to 0.0207 times 3 power. All right, so as always, I invite you to calculate this value on your own. And if you do, you should end up getting $7,980.52. All right, so we see that at the end of 3 years, we're going to earn about $480.52. Now we want to talk about a zero coupon bond. Not coupon. Let's fix that. Coupon. A zero coupon bond has no interest payments during the life of a bond, as opposed to corporate or I don't know how to say that word, municipal bonds, who usually make semi-annual interest payments. All right. So for example 5, we're going to find the face value of the zero coupon compounded semi-annually 30-year bond at 6%, sold for $2,546. So we're going to use our equation that we had before, where we had A is equal to P times 1 plus I to the n power. And we have that P is going to be equal to $2,546. We have that I, since it's going to be 6% semi-annually, we're going to say 0.06 divided by 2. And then, since we're doing semi-annually for 30 years, that means that our N is 30, but since it's semi-annual, that means twice a year for 30 years. So it's going to be N is equal to 30 times 2, or 60. So your N value will change depending on how many times per year and then the amount of years. So we can end up calculating this value, and we see that we get A is equal to 2,546 times 1 plus 0.06 divided by 2 to the power of 60. All right, so I encourage you to calculate this value on your own. And if you had, you should have gotten a value extremely close to $1,500, $15,000. So this means that our face value of our zero coupon compounded semi-annually 30-year bond at 6% that ended up selling for $2,546 was going to be $15,000. So that was the face value of our zero coupon bond. All right, so now we can move on to our next example, example 6 here. We're going to suppose the inflation rate is 2.7%, meaning the overall level of prices is rising at 2.7% a year. How many years will it take for the overall level of prices to double? So if we're thinking about how many years it will take for our inflation prices to double, all we really need to consider is how long it will take $1 to become $2. There's no need to make up any crazy values or anything along those lines. You can just choose $1 and $2. So then we can just take $1 as the present value and $2 as our future value. And if you remember, our future value, which we called in our last equation on it, is going to be A. And we know our present value is going to be P. All right. So now, let's use our compound amount formula, our compound interest formula, which we know that is just going to be A is equal to P times 1 plus I to the n power. All right, so now since we're using 1 as our present value and 2 as our future value, we can plug these values in. So we end up getting 2 is equal to 1 times 1 plus I, which is going to be 2.7%, so 0.027 to the n power, since we're trying to find how many times a year it will take, or how many years it will take for the overall level of prices to double. We're going to assume that this changes annually. All right, so now since we have this value here, we know that 1 times anything is just going to be whatever you're multiplying it by. So our equation here is going to become 1.027 to the n power is equal to equal to 2. Sorry. Oof. All right. So now that we have 1.027 to the n power, I'm so sorry. All right. Oof. Okay. Now since we have this value, we know it's to the n power and it's going to be equal to 2. So we can graph this in Desmos, or we can solve this algebraically. All right, so let's solve this algebraically first, and then we can go ahead and see if we can solve this in Desmos. All right, so if we want to solve this algebraically, and let's just pull this over here so we have some more room. We have 1.027 to the n power is equal to 2. So if we want to solve this algebraically, and a property that we learned was our power property of logarithms, which we can use for exponential problems, we can use that in order to take the natural log of both sides So now we can take our n value and we can multiply this to the front of our equation. We can get n times the natural log of 1.027 is equal to the natural log of 2. And now, just to solve for n, we're going to divide each side by the natural log of 1.027. So natural log of 1.027. So now we know that n is equal to the natural log of 2 divided by the natural log of 1.027. So I invite you to calculate this on your own. And if you do, you should end up getting 26.02, or we can say about 26 years in this case. So you can say it will take about 26 years for the overall level of prices to double. All right, so now let's go ahead and see if we can find this value now in Desmos. All right, so now we're in Desmos, and I've already plugged in our equations here. So we're using y is equal to 1.027 to the x power. And then we want to set y is equal to 2, since we want to know when our values are going to double or become 2 if we're comparing with 1. So we see here we have our graph, and we just need to scoot all the way over, and we see that at 26.017 or 26.2, we will see that our prices will double. So we still get about 26 years. So that's just a really quick and easy way to check if your answer is right, or to just see if you can find the answer using Desmos. All right, so I'm just going to draw your attention back up to our continuous compounding interest. I realized that I think I forgot to include the continuous compound interest equation initially, although we did use it and I ended up highlighting it, but let's highlight that just a little bit more so we know. But we see here I have now included the definition. So our definition of continuous compound interest was the continuing compound amount A for a deposit of P dollars at an interest rate R per year compounded continuously for T years is given by A is equal to P times E to the power of R times T. So we did use that value there, but that is the official definition, and so you'll see that in the notes eventually. All right, so now let's scroll on back down to where we left off. So we see here we have what was called the effective rate, or the APY. So if you invest $100 at 9% compounded monthly, and at the end of your year, we're going to end up getting, once you calculate everything, you'll end up getting $109.38. Then this means that you earn $9.38 of interest, which is 9.38% of your original $100. This means that if you invest $100 at 9.3% compounded annually, this is thinking about simple interest, then this will result in the same amount of interest that we had if we compounded monthly. So in this situation, a 9% interest rate is called the nominal or the stated rate, and 9.38% is called the effective rate, or the annual percentage yield. So this is just thinking about if we compound, annually, monthly, semi-annually, some sort of compound interest rate. If we take that compound interest rate and then we find how much interest we earned, and then we calculate that into a new percentage, that means that if we take that new percentage and we do a simple interest rate, we would end up with the same percentage. These interest rates are called different things. So your first interest rate that you will use with a compound equation, that would be your nominal or stated rate, and then your 9.8 or 9.38% or whatever percentage that you found later, that would have been your simple interest to get the same value. That would be your effective rate or your annual percentage yield, which is called your APY. All right, so your APY, or your effective rate, R sub E, is the annual compounding rate needed to produce the same amount of interest in 1 year as the nominal rate does with more frequent compounding. So your effective rate, APY, it corresponds to a stated rate of interest R, compounded M times per year is, and then we have our equation here. So our effective rate equation is going to be 1 plus R divided by M to the M power minus 1. So we have R, whichever our rate is, divided by the number of times per year, and then we raise that value to the power of however number times per year that you compounded, and then you'll subtract 1. So let's put this into practice. We have example 7 here. So we want to find the APY corresponding to the given nominal rate. Just one single rate here, not multiple rates. Great, there we go. All right, so we have 4% compounded semi-annually. So we know that our rate is 4% or 0.04. Our M value is going to be 2 since we're doing semi-annually. And those are all the things that we need to know. We only need to know our rate and the number of times we compound per year. So using this equation, we want to find our effective rate, which is equal to 1 plus 0.04 divided by 2, since it's going to be R divided by M to the M power, so 2 minus 1. So if we calculate this value here, we're going to end up getting R sub E is equal to, if we just simplify what's inside our parentheses, this is going to be 1.02 squared minus 1. Let's bring this up here. And if you calculate what is in our parentheses, or you square that value, we'll end up getting 1.0404. We're subtracting 1, which means that our rate effective is going to just be 0.0404, or writing this as a rate, it's going to be 4.04%. So we see our effective rate is very similar to our nominal rate, which we were given, which was 4%. And so we see that they are very close together. All right. So now let's get into our present value for compound interest. So we see that our present value for compound interest, the present value of $8 compounded at an interest rate I per period for n periods is going to be P is equal to 8 divided by 1 plus I to the n power, or you can just rewrite this as P is equal to A times 1 plus I to the negative n power. So you can write it however way you want. But if you notice here, our present value for compound interest, our original equation for compound interest was just A is equal to P times 1 plus I to the n power. So if we want to find P, or isolate P, then all we need to do is divide by 1 plus I to the n power. And we get P is equal to A divided by 1 plus I to the n power. So to find your present value for compound interest, all you need to do is just single out and isolate your p-value, which you originally had in your compound interest equation anyways. So this is just a reframing. And what you're going to see with a lot of these equations that we've been going through in this section and next section, also last section, is that a lot of these equations are just a manipulation of original equations that we've learned. So it's a lot of just rewriting, reevaluating, and solving for different values. So now we have our present value for compound interest. So this is just going to allow us to find a present value if we know what our future value is going to be along with our rate and how many times we compound per year. So this is essentially letting us work backwards. So for example 8 here, what did a $100 item sell for 5 years prior if the annual inflation rate has been 3.2%? So we want to use this equation up here. So we know that A is equal to 100. Our N, since it's an annual inflation rate, that means that it's just one time per year. So we know that our N is equal to 5. I realized that I missed a 0 when I wrote this problem. So it's $1,000, not 100. 1,000. There we go. And our interest rate is just going to be 0.032 since our N value is 5, and we're doing this annually, so we don't have to divide our interest rate. Well, we do. It's divided by 1, which gives us our original interest rate. So now we can find our present value. So we get 1,000 divided by 1 plus 0.032 to the 5th power. And if we just want to simplify whatever is inside our parentheses, this just gives us 1,000 divided by 1.032 to the 5th power. And I invite you to calculate this value on your own. And if you do, you should end up getting $854.28. So this means that a $1,000 item sells for 5 years prior, a $1,000 item in 5 years prior will sell for $854.28. So we see that in just 5 years, our value of this item is going up about $150. So it's definitely important to check out those inflation rates. All right, and just a quick summary because there was a lot of content in this section that we had to go over, and a lot of kind of like revisiting older terms and giving them new definitions and everything along those lines. So let's just do a quick summary. So we have that at this point, it seems helpful to summarize the notation and most of the important formulas for simple and compound interest. So we see that P is often utilized as a principal or a present value. A is usually our future or maturity value. This isn't two different things. It's just that we call it sometimes a future value and sometimes we call it a maturity value, but A will always be known as a future maturity value, whereas P can be principal or present value. We see that R is our annual interest rate. So we'll now see R as kind of like a stated or a nominal interest rate instead of like per period. So R is going to be used for annual things. Then we have T, which is our number of years, M, which is our number of compounding periods per year. Then we have I, which is our interest rate per period. So I, as opposed to R, we just have I is our interest rate per period. So whatever period you have, and the only difference is that it's not annual. So R is just used for annual, so that once a year, and then I is used for anything that's not once a year. Then we have N, which is our total number of compounding periods. So this means that our N value is going to be however many periods for a certain number of years, where our value of M is just our number of periods per year. So if it were quarterly, our M would be 4, but if we said quarterly for 2 years, then N would be 8. Then we have our R sub E, which is just our effective rate or our APY. So then our important calculations that we have here is simple interest, which is just A is equal to P, or our future value is equal to our principal times 1 plus our annual interest rate times our number of years. And then below that is just a rewriting. So if we need to define our principal instead of our future value, we would just have principal is equal to future value divided by 1 plus our annual rate times the number of years. Then we want to think about our compound interest. So this means that our future value is equal to our principal, or our present value is more often called, times 1 plus our interest rate per period to the power of the total number of compounding periods. Then we have our present value, which is just, once again, the rewriting. If we needed to find a present value instead of a future value, is just going to be P is equal to A divided by 1 plus I to the n power, or which is the same thing as writing A times 1 plus I to the negative n power. Then we also have our effective rate, which is going to be 1 plus R divided by M to the n power minus 1. So we see that our effective rate really depends on the number of compounding periods per year and not by how many years. So it's important to recognize the difference between that N and the M. Then for our continuous compounding, this just gives us the equation A is equal to P times E to the power of R times T. And then if you want to rewrite that, it's the same thing. You would just solve for P instead. So you have P is equal to A divided by E to the power of R times T. All right, so this section was a tad more difficult than our last section on simple interest. So if you have any questions at all, please do not hesitate to email me, drop into my office hours, submit one of the anonymous questions in your question form, or anything along those lines. So I will see you virtually all later.